remember in the very first video of this section I mentioned that the only main required integration knowledge that we are going to use for this section is the integral of f prime over f is equal to the modulus of ln of the modulus fx, right? So this is the only basic equation that we are going to use in this section, throughout this section. Okay, right. Say for example, if we have let's say x squared plus 1, and if we have 2x in here, then the answer for this integral will be x squared plus 1 plus c, because it has this property. And what if we have something like this, x squared plus 1 and x in here, right? Now directly we cannot see any such relationship as it was in the previous example, because the derivative of this denominator is 2x, but in the numerator you have x. So what we can do is we can simply write 2 here, and to counterbalance it we need another 2 in the denominator. So the answer will be equal to half times ln. The answer for this one is the same as before. Okay, right. Now what if we have something like this one, x cube plus x over x minus 1, or like now here it is an improper fraction, right? So now basic idea or the key point that you should focus here is that in these cases we were dealing with polynomials in both numerator and denominator, but for this equation to be true, you don't have to have polynomials in the numerator and the denominator. But in the case of polynomials, we can get help from another source that we learned, which is partial fractions. Okay, so that's the place where we are going to link the two. The partial fractions and the integration is linked when you have to find integrals of rational functions. Rational functions in the sense something like this format, where you have a polynomial in the numerator and a polynomial in the denominator. So when you are supposed to find the integral of these sort of things, what we should do is we should go for the partial fractions. Now for these kinds of things, if you can directly extract out the derivative as it was in the second case, right? Now here you don't have to go for any partial fraction thing, right? You can directly write down the numerator, and to counterbalance it you can write this number in the denominator and directly use the theorem that I mentioned above, right? But now for questions like this, you don't have that relationship at once. Okay, no matter what number you like, no matter from what number you multiply the numerator, you will not get the derivative of the denominator. Okay, so here as the first step we should go for partial fractions. Okay, so from the partial fraction knowledge we know, now see here, this is a improper fraction. Okay, and we learned how to deal with those kinds of fractions. Then the partial fractions will be equal to this one, right? So now for this one we can easily handle, right? We can have the answer for this one because it's just a polynomial. And for this portion, we have a number in the numerator and a linear factor in the denominator. So what we can do is, if we just take this 2 out from the numerator, from the integral, we have the denominator as fx and the numerator as f prime x. So the answer will be the integrals of these functions, and for this one it's ln x minus 1 plus c. Now this is the second example that we discussed. Here, in this case also, if you try to see whether you have this relationship at once, you might not be, like, it's not true, because the derivative of this one will be 6x squared plus 6x minus 2. Okay, so you cannot multiply the numerator by any number so that the numerator will be equal to this one. Okay, so then what we should do is, we go for partial fractions and then simply integrate the term, but like integrate these partial fractions separately. And here you can see at once, although you don't have the derivative of the numerator, what you can do is, you can multiply it with 2 and you can divide it by 2, so this becomes 10. Then you will have the derivative of the denominator in the numerator, so this will also become ln mod of 2x minus 1. And here for this one, you have the partial fractions like this, and then by doing the calculation we have this result, and from here to here we use the logarithm rule of where if you have ln a minus ln b, you can write it as ln a over b, right? Now here we have now initially I didn't write the modulus sign, so we should get this one. So we will have L mod of a divided by mod of b for ln, and this can also be written as a divided by the complete thing with the modulus. Okay, because these two are equal, and also of course you have to write the ln term. Okay, and then the next result. Now in all these results you can see that you don't have this relationship at once. Okay, so since these are polynomials, we go for the partial fractions. Okay, right. And the next example is this one, where you can see that it is a improper fraction, and so once you get the partial fractions, you have like it has a repeated linear factor, and by doing the integration you can get this one. For the integral of this portion, we are not using this result, okay, but it's just a simple integral. And also we can combine these two terms to form this one by that result I mentioned before. Okay, this is equal to ln a over b, right? Okay, the next example is this one. So once you get the partial fractions, you have this, right? And then you can see for the integral of this term, you can write the log of mod x, but for this one still you don't have this relationship. So what can we do? Now for this term you cannot simplify it any further through partial fractions, because this is a irreducible quadratic term. That's all we can do, right? Therefore what the next thing that we can do is we can just separate out the denominator into each of these two terms. It's like if we have a plus b divided by c, we can write it as a over c plus b over c, right? So this together with the denominator we can write a separate term, and the same denominator together with the other term we can write a separate term. And now you can see for this one the derivative should be equal to 2x, and here you have x, so we have this alteration, right? It's, yeah, actually although I said alteration, we are not doing any changes, okay? It's the same thing, but we are writing it in a different format, okay? And so the answer for this one will be half times the log of x squared plus 4. And for this one we will have to use another standard integral result, okay, which is the derivative of, sorry, not the derivative, the integral of something like this is equal to 1 over a tan inverse x divided by a, right? So this is a standard result, and we have the same format for this integral, right? So we can write it as half times tan inverse x by 2. Okay, also don't forget to mention this c when you are doing the indefinite integrals, right? The next example will be the improper fraction, this one. Now see here, the degree of the denominator and the degree of the numerator are the same, okay, but still we call it as an improper fraction, okay? If the degree is like if the degree of the denominator is greater than the degree of the numerator, we call it as a proper fraction, okay? But if it is not the case, that means if it is less than or equal, then we call it as a improper fraction, okay? Right, so in this case also it is an improper fraction, so we can do the long division, right? Now once we do the long division, we are at this position with these two terms. But here the thing is, you can see that for this term what we normally do is we do the integration by parts. But the problem here is for this term this is a irreducible quadratic term, okay? You can see the b squared minus 4ac term here, where a is equal to 4, b is equal to minus 4, c is equal to 3. This term is less than 0. That means this is an irreducible quadratic term. Okay, so we cannot find any further partial fractions for this one. And on the other hand, this is not of the format f prime over fx. Okay, so what should we do for this term? Right, now this is kind of a new thing that we are going to learn. It's not a difficult thing, or it's not a long theory part. It's just a small calculation that we should adopt when you have a irreducible quadratic term in the denominator, okay, and when you have a first degree polynomial in the numerator, right? Okay, so the method that we are going to do is we complete the squares of the denominator. That means this is the denominator, okay? So can we write the denominator as a square? At once we can. It's since this is irreducible, and if we were able to write it as a square of a certain thing, that means this has factors, right? If a is a real number, then that will imply that this polynomial has factors. Okay, in other words, this polynomial will have roots if this is equal to a square like this. Okay, and at the beginning we said it does not have any roots. Okay, but what we can do is we can complete the squares. That means, what if we write it like this, right? The reason for choosing 2x minus 1 is because when you expand this one, what you will get is 4x squared minus 4x plus 1. See, you have already obtained both these terms by squaring this one, right? But for the constant term, you have only 1. Okay, so the answer for this one is equal to this. Okay, so these two, this one and this one, is not equal. But see, what will happen if I add another 2 for this term? The answer for this squared expression is this one, and if I add another 2, then the total constant value will be equal to 3. That means the left hand side and the right hand side are equal. So basically this is equal to the given original polynomial. Okay, and this method is called completing squares, right? And once you complete the squares, what we can do is, now the problem at our hand is this portion. Okay, we know the integral for this one, which is equal to x, right? And for this fraction, what we have already done is we have written it like this. Okay, so what we do next will be we use this substitution. Okay, and then when for a substitution to work, that means we are converting everything in terms of u. So we have to replace everything by u and du terms. So to find the corresponding du relationship with dx, we need this one, and then from the first equation you can see that x is equal to half times u plus 1. So we substitute both these terms in here. Now as you have only dx, you have to write 2 and half here. Okay, so for this, instead of this term you can substitute du, and for all the other x terms you can have this one. Therefore you can simplify it like this, and once you have this step, you can separate the denominator into each of these two terms, like the one that we did before, right? We can write it like this. Okay. You can do the calculation like this. So now here we have f prime x over fx, but be careful, you have to put 2 here and then you have to divide by 2, and for this one we use the result of the integral with the tan inverse, right? So this one you can visualize it as the square of root 2. So for this you will get tan inverse u over a divided by a. Okay, right. Now so from this one, from this calculation, we can kind of generalize a certain thing where we can come up with a certain general method of dealing with the situations where you have an irreducible quadratic term in the denominator. Okay, so when you have an irreducible quadratic term in the denominator, and if you have a numerator which has degree 1 or less, okay, if it is less, like if it is just a constant, something like this, if it is just a constant, we can use that tan inverse thing for the integral, right? But if it has another, like kind of a first degree polynomial, what if it has a second degree polynomial? Then it is an improper fraction, so you can do the long division, right? So the only problematic situation is this one, the case where you have a quadratic irreducible expression in the denominator and a first degree polynomial in the numerator. Okay, right, and also the irreducibility is important, okay, because otherwise you can factorize it and go for long the partial fractions, right? So if it is of this nature, irreducible quadratic polynomial in the denominator and a first degree polynomial in the numerator, but anyway if you write it like this one, it will anyway be irreducible, okay, because you don't have any roots for this expression under real numbers. Okay, so if that is the case, what you can do is you can write it as u squared plus a squared and d u squared plus a squared, and for this one you can write the you can visualize it as in this format, right? Only thing is that you have to multiply it with 2 and divide it by 2. And for this one we can use that tan inverse formula for the integral of this portion. Okay, so it's kind of a general result that we can adopt when we are doing the integrals. Okay, right, and in the next video I will discuss some 2 special cases and then we can conclude our section.